Now in problem C, we have a more complex compound. So in order to alleviate sort of the difficulty, we need to first do two things: identify the chiral centers and draw in the hydrogens so we can imagine what's going on. So if we start with this compound, the first thing we observe is that the hydrogens are projecting outwards on wedges, so we need to make the switch before we do anything. And then let's analyze our four different groups at carbon 1. So we have a carbon triply bound to nitrogen. If we go down, for our first step, we have a carbon, and then second step, a nitrogen singly bound. And if we go towards the left, we have an sp2 carbon. So after looking at all four different groups, the nitrile group takes first priority due to the number of bonds. Coming down here, the amine group, it would take the second highest priority because it's singly bound. Hydrogen, of course, takes last, which is right here, and this sp2 carbon takes third priority. Now we draw an arrow from 1 to 2 to 3. It looks like we're going in a clockwise motion, so really it's S at carbon 1. Now at carbon 6, the amine group, because of atomic number, takes first priority because it's directly attached to the chiral center. So if we go upwards, we have a carbon bound to a carbon, bound to a nitrogen triply, and if we go down here, we have a carbon bound to a carbon, bound to an oxygen. Now we need to be careful because the first point of difference was not the heteroatom. It was actually the first step, the first carbon we encounter emerging from the chiral center. We have a CH2 group here, and if we move upwards, we have a CH, which is then bound to another carbon, triply bound to nitrogen. So because this is a secondary carbon versus a tertiary carbon, because it's bound to 1, 2, 3 carbons compared to just 1 and 2 here, this group takes second priority, and this group here, going down to the bottom left, takes third priority. Now we just draw an arrow from 1 to 2 to 3 in our minds. It looks like we're going in a counterclockwise motion, so really it's R at carbon 6. Now on the second stereoisomer, we have higher priority groups projecting towards the back, and hydrogens, the universally lowest priority group, projecting out at us, coming out of the plane. So we need to make the switch before we do anything. So at carbon 1, if we analyze the four different substituents, we follow the same thing we did here at carbon 1. It's these turquoise numbers. So the nitrile takes first priority just like it did here. The second highest priority group was this one here, where we went down, saw a carbon, and then it was bound directly to a nitrogen singly. So that would be the case here. This group would take second priority. The hydrogen, of course, takes lowest, and this group by default takes third priority, just like it did here. So then we just draw an arrow from 1 to 2 to 3. It looks like we're going counterclockwise, and because we made a switch here, we need to reimpose the switch. So counterclockwise really means R at carbon 1. Now at carbon 6, again, we do the same thing we did here. This time we look at the pink numbers. So at carbon 6, if we emerge from the chiral center in all four directions, of course the hydrogen is lowest priority here, and the amine group takes first priority. And using the first point of difference rule, we have CH2 here compared to a CH, which is then bound to another carbon. Again, it's a secondary carbon versus a tertiary carbon. So this group here takes third priority, whereas this one takes second. Then we just draw an arrow from 1 to 2 to 3. We're going in a clockwise motion, but because of the switch again, it really is S at carbon 6. And if we look at the chiral centers, finally, 1s, 6r versus 1r, 6s. These are enantiomers. One way to check your work and to prove that these are enantiomers, or in other words, mirror image molecules, is to look at the symmetry. We have the double bond and the carbonyl pointing straight down and towards the right, whereas here, if we rotate this molecule a little bit counterclockwise so that the carbonyl points straight down, we'd have the double bond pointing towards the left. So if we have the double bond towards the right here and the double bond towards the left here, you would see that these are mirror image molecules. So in these cyclobutane derivatives, we have a fluorine bound to carbon 1 and a methyl bound to carbon 3. Now, if we even attempt to look at stereochemistry, we need to first ensure we have chiral centers. Now, if we emerge from this supposed chiral center, we would have a hydrogen projecting towards the back, a CH2 group, and then this tertiary carbon. If we go the other way, we'd find a CH2 group and then the tertiary carbon. So because these two groups going down or going towards the left end up at the same spot at step 2, we don't really have 4 unique substituents. So this carbon here is not chiral. At carbon 3, it's the same story. If we move to the right and towards the top, the first step we encounter a secondary carbon, the CH2s here. If we continue on to step 2 for both of these, we end up at this secondary carbon bound to fluorine. So this carbon isn't chiral either. So individually, this molecule can be considered achiral. We don't really have a chiral center. And if it's achiral here, this molecule is achiral as well. The only difference here is that we have the fluorine going into the plane, whereas here it's coming out, and the methyl group here is projecting outwards, whereas here is projecting into the plane. So we need to visualize in 3D space to really compare these molecules and assign the appropriate relative term. Because I suspect that these two compounds could be the same, but I need to prove that. So I'll take this compound and rotate it counterclockwise so that the methyl group is now in this kind of orientation and the fluorine is now pointing towards the top right. So now that I've done that, what I can do is to rotate this molecule 180 degrees, a full flip in other words, and I'll use this as my axis. So basically, I'm taking this portion of the molecule and sending it that way, and I'm taking the fluorine and pulling it back this way, so it's a full 180 degree turn. So once we have that, we're really close to getting this molecule. All I need to do now is to rotate it clockwise or counterclockwise and send this fluorine from the bottom left to the top right. And I'll bring this methyl group from the top right to the bottom left. All I do is just to rotate on this plane, rather a full 180 degrees, clockwise or counterclockwise. So it looks like I ended up with the same exact molecule, even though both of these are individually achiral, they don't have chiral centers. Compared to one another, these are the same molecule. Again, achirality refers to no chiral center present on the molecule. I can have a cyclohexane, which is then bound to an OH up here, right here, and here. The key in looking for achiral compounds is often you'll find some sort of symmetry, even though it's not necessarily meso. So we have an OH, a hydrogen projecting towards the back, and if we go left or right, we encounter a CH2, and then this carbon bound to an oxygen. Same thing here, CH2, carbon bound to an oxygen, and we end up right here at this secondary carbon. If we go either way, left or right, it's the same story with this OH and this OH. So this compound is achiral because it lacks a chiral center. This cyclopropane derivative is also achiral. If we imagine putting an OH group here, let's say a butyl group like that, really there isn't any chiral center. The two unique substituents are the OH and the butyl, but if we come down here, we have a CH2 as well as a CH2 here, and ultimately we don't have a point of difference, so there's no chirality in this compound.